Yes guys, welcome to my YouTube channel, Pure Math School. And here we teach pure mathematics. And basically today we're going to start with the first video. That's our first topic, or the beginning topic, the introductory work. And the following are the subtopics we're going to handle. We have the number line, inequalities, basic algebraic manipulation, surds, quadratics, trigonometrical ratios of acute and obtuse angles, solution of triangles, three-dimensional trigonometry. And today the first thing we're going to handle is the number line. And so let me first draw how a number line looks like. That's it. This 0 is our origin, and on the right of the 0 we have numbers that increase from 1, 2, 3, 4 until infinity. And on the left we have what we call negative numbers. Let's start from -1, -2, -3 until negative side of infinity also. And on the right of the 0 we have numbers increasing as you go to the right, further to the right of the 0. And on the left, as you go further to the left of the 0, we have numbers decreasing, increasing here, decreasing this side. And if we happen to, one thing we need to know about the number line is that at the right of every number, or at any right of every point, the number is always bigger than on the left. For example, if we take a look at this point, say 2, the number on the right of 2 is bigger, that's 3, compared to the number on the left of 2, 1. And even if you take another one, let me say -1, we all know that 0 is bigger to -2, because 0 is on the right of -1 and -2 is on the left of -1. And that's basically, now we're going to be looking at what makes this number line complete. That will be looking at the different numbers that are found in this number line that makes it complete to be used for future use as we introduce it today. Now, as we see, as we learn to count, initially, we use numbers, that is numbers from 1, 2, 3, 4, 5 until where you can possibly end. And these numbers are referred to as counting numbers or natural numbers, or positive integers. Positive integers, we can give, it has a symbol, that's Z. That's its symbol. But you know, as our use of number progresses, we need to include other numbers into play. That is, we have to extend these numbers backwards to include 0. We're going to extend the numbers, counting numbers are from here. So as our use of numbers progresses, we have to extend backwards to include 0 and the negative numbers. So if we include 0, if we include 0 and negative numbers, we have a set of integers that's z. We're using this figure here. We had positive integers, but now we don't have a plus on top of that z. So we have a set of set of integers that come from some negative values far, and to maybe closer ones that we can know: -4, -3, -2, -1, 0, to the positive ones: 1, 2, 3, until where you can reach. And now, but we know that this what we basically have on the number line right now. We have positive integers, negative integers, and the 0. But we know that this is not sufficient for many purposes. So we include fractions, and these fractions are into two. That's to say, we have rational numbers and irrational numbers. To begin with, rational numbers can be expressed in the form a over b, whereby we have a and b being all integers. This symbol simply means being a member or belonging to. So whereby all a and b being all integers except for b equals to 0. So if you can express any integer in this form, a over b, that means you really have a rational number. And we have to note that a over b must be in its simplest form, meaning there shouldn't be cancellation of or reduction of the fraction. So another thing we have to note that is that here all integers are rational, since for any AB being a member of the integer, the set integer, can be expressed in the form a out of 1. So that means if you can express, that means if you look at our number line, these numbers that are in the number line, we can see that all of them have 1 under, 1 under, 1 under, 1 under, all of them. that makes them a fraction, and all of them are rational if they can be expressed in this form, because the only thing that limits is if b is a 0. But so we only, if our b is fixed to be 1, that means we have all integers are rational numbers. So we now advance to irrational numbers. For irrational numbers simply can't be expressed in the form a over b for a and b being integers and b not being 0. So rational number is simply the opposite of rational numbers. You can't express in the form of that. And maybe an example you can give would be root, let me say root 2. So we have that root 2, and we can prove that. I think for this case we need to prove that it's not rational. That means we need to show that it cannot be expressed in this form. And remember, it has to be in its, this a and b should be in its simplest form. So if you can't prove that this one is in its simplest form, then that means it's basically root 2 is basically irrational. But we're going to prove this by contradiction. That means at first we are going to prove that we are going to assume that what we want to prove is not true. Then later it will lead to a contradiction. Then we just conclude that what we are actually proving is true. So we're going to use proof by contradiction. So that means, I told you, by contradiction we first assume what we intend to prove. That is what we intend to prove that root 2 is irrational, is not true. So we first assume that root 2 is irrational. That means we assume root 2 is rational, which implies root 2 can be expressed in the form a over b. You can simplify this. We square both sides to remove the root, remain with 2 being a squared out of b squared, so that we have a squared equals to 2b squared. We can name this maybe equation 1, so it might help us ahead of time. So now equation 1, we have a squared equals to 2b squared. This, if you can see that from here, we can see that a squared is even, since it's multiplying integer square of the integer b by 2. And you know, any number that can be, if any, that means a squared is actually a multiple of 2. Any number which is a multiple of 2 is even. So that we know that here we see that a squared equals to, is even, which implies even a is even. Why? Because you can, if you square an even a square of an even number, if a square is an even number, that means if where it came from, that is its root, is also even. That's the simple thing I can say about that. So now, since it's even, since a is even, that means a can be expressed in form 2 times some integer, let me say k. For k being an integer, this one is just meaning for every k, this sign, meaning for every k being a member of an integer, member of the set integer of integers. So if we can substitute for a in that equation 1, substitute for k in equation 1, I mean a, sorry, a for a in equation 1, that means here we're going to have 2k squared. Substitute here we're putting 2k in place of a equals to 2b squared. So here we can open this and expand this bracket. That means we have 4k squared giving us 2b squared. So we can divide both sides by 2 to reduce this, since it can be reduced. We have 2k squared giving us b squared. We can see that b squared is even, since it's also multiplying integer, the square of the integer k by 2. So since multiplying the square of the integer k by 2, it implies that even b is even. Now we have both the integers a and b being given here. We saw that a is even, we also saw that b is even here. What does it mean? That means there must be, if we happen to express in the form a over b, that means a and b are supposed to cancel out. I mean, not cancelling out totally, but at least there must be reduction of the fraction, which proves that this implies a over b is not in its simplest form. It is a contradiction of our assumption that root 2 is rational. Therefore, root 2 is irrational. So we are done with that proof. We can see that root 2 is irrational. An irrational number must be in its simplest form, and since we could not see that a over b is in its simplest form here, we had to conclude that it's irrational. Now I just have a few things you can note before I conclude this video. Let me note for you some things here. Now with let me say a set of rational numbers together with irrational numbers form the set of real numbers, which you can give that symbol with that bar, and then when in a number line, for it to be complete, must constitute real numbers. So since we have rational numbers together, the rational numbers completely forming up a set of real numbers, that means we can actually now have our number line complete, implying the number line is complete. And another note that I can give is a note that if we express numbers, if we say we express numbers as decimals, so expressing numbers as decimals, we realize that rational numbers sorry, not rational, not real, rational numbers have finite number of decimal places, or will recur. By recurring, I mean repetition. I can say 0.12, then maybe 2 repeats. That's what I'm meaning by recur. So by this I say 2 is recurring. And for the case of irrational numbers, we'll have infinite, that means uncountable, infinite numbers left here number of decimal places without recurring. That means no repetition, but you can, the numbers are changing, but like this can be 1, 2, maybe 3, 5, 6, 7. They're just changing like that, but without repeating constantly like this. So that's basically, so infinite number of decimal places without recurring. While for rational numbers, either they will have finite number of decimal places or will be recurring in case it's not a finite number of decimal places. And I think that's all we can have for today. Thank you for coming to my channel. Please like, subscribe, and share my video, and please see you in my next video.